said, hey, what's this? They claimed that it was a security measure to reduce the popularity of the application, so that I guess if the FBI started coming after him, he could release this master password to the world, and suddenly everyone would hear about it, and then the people running it would, would basically take it down, or not want to use it anymore, and therefore the overall impact of the footprint of this thing would decrease, and the FBI wouldn't care anymore. I don't know. It doesn't sound like a very likely story. But he did acknowledge that there was a master password there. Same for sub 7. It's just again, it's just a long string, just embedded in the application that after it compared against the configured password, compared against the master password, and if that was provided, then just let the guy in. And here's the disturbing one: exploitable vulnerabilities. If you want to put a backdoor in a program, you could do any of these other things that we've talked about. You could, you could put a hidden parameter in there. You could make it call out. You could, manipulate parameters, whatever. What if you just embedded a vulnerability? What if you just, what if you just wrote a function that had a stack overflow in it? Well, I mean, technically, if you make it easy enough to exploit, if you, lay out the stack properly, or you put it in a location that's called from the right places, and you can make vulnerabilities more or less exploitable depending on where they are and how they're called. You could write your input validation, your security, your actual security function, your input validation. You could write a regex that isn't quite correct. Regex are really complicated. It could be something that looks good enough for the auditor to get past code review, but in certain circumstances you can fool it. They're so complicated that that sort of thing would be likely to get through. So this kind of the idea of a vulnerability as a backdoor is kind of blurs the whole definition of what constitutes a backdoor. And what it does is it may not be as straightforward to exploit, but it gives the person who did it a level of plausible deniability. If somebody comes to me after I put this stack overflow in that could be it's integer overflow or whatever, and they say, look, somebody could take over the system with this, I can just say, oh, I didn't know I shouldn't use getS, and it basically just looks like a developer mistake. Now you can only do that a few times before you get fired for incompetence, but you can see it's not quite as cut and dry as, oh, there's this parameter that calls system. You can't really prove that I intended to put the vulnerability in. So technically, any vulnerability that's ever been discovered in a piece of code could have been a backdoor, but So, what time is it? 5:45. Okay. So one thing that we did as part of this was just to write a quick proof of concept of the idea of using static analysis in an automated fashion to detect certain patterns. So we wrote in IDA a script for one of these categories, and what it basically does, it was one of the ones that Chris talked about in his section, which was looking for static strings being passed into crypto functions, and that's what was used in the Borland interbase backdoor. So what we can do is we can start with all known crypto APIs, look for calls to that, look at the parameter that we know is the sensitive one, and then trace that back using IDA to figure out if it's a static string or not. So let me pull up something real quick here. What we basically did for the purposes of this is that we just took some open source FTP program and inserted a backdoor in that. So let me clarify, pure FTPD does not have a backdoor in it. We put this in for the purpose of this. I'm going to pull up this file. Actually, let me talk about the script first. It's loud. So what the script basically does is, like I said, it looks for all instances of a set of crypto functions, and those are basically kept in a data file. So it's pretty straightforward. It's just by name. So the first word is the function name, and then the number out to the side of it is which parameter we're looking to see if it's a static, a constant string. So if the first parameter to crypt is constant, then flag that, and so on. You can see that all the OpenSSL API functions are here, and a couple other APIs. Here's some Win32 specific stuff. Obviously, this can be very easily extended, especially if you've got your own custom APIs that you're using. So this is the data file that the script uses. And basically, what we do is just open up your binary in IDA. Okay, and then you load up your script. It asks me where the file is with all the functions that I care about. Pick that. And then you can see down here, basically it just says here are all the addresses where a constant was pushed to the function, and there's where all the function calls are. So I can double click on each one of these to be taken to where that happens in the code. I don't like this mode for this. Put it back in text view. So here I can see that a constant was pushed into EAX, and then it was put at ESP+4, and then crypt was called. So there's this weird string here, with a bunch of numbers and dollar signs in it. So I'll look at each one of these. Okay, in this case, it's passing in something similar. More stuff that says test, calling crypt on that. This last case, here's our backdoor. I'll pull up the source tree of this in a minute, but this one, you can see it's passing in BH2007 as the first parameter, and XZ as the second parameter, which is just the salts. It doesn't matter. And then it's calling crypt. So that's all four of these at the moment look suspicious because we don't know what those first ones are. But now we can pull up the code and actually take a look at it. So in this case, we took the same approach as the Borland guys and just said, basically, this is the function that parses through. There's a password file. So pure FTPD has the notion of virtual users. So like I'm running the server on Windows, I don't need to have every FTP user mapped to an actual system user. I can create basically a password file that has virtual users, and then once I have that password file in place, I have to run this executable pure PW with a make database command, and then that takes the password file and creates the actual password database that pure FTPD uses. So this is the function that parses that file and creates that database, and you see there's a loop that goes through all those, and then at the very end it calls crypt on our BH2007 password. It does a sprintf, which is you can kind of see this is password file syntax, and then it calls the function that adds that set of credentials to the database. So no matter what you do, when you call this make database functionality, it's going to stick this one at the end. So you can see how that was pretty easy to detect just based on known API calls. That could have been any that could have been des and crypt or any sort of function. As long as we're looking at the right parameter, we'll find those uses. If we want to look at the other ones, basically the other ones actually are tests. They are in there. It's just basically does a crypt and it compares the output of the crypt function to what it expects the output of the crypt function to be. So I won't really dwell on those. But you can see how this would be pretty easily extensible to some of the other detection mechanisms that we talked about. simply because a lot of them do focus on known APIs. And you're going to be looking for different things in each case, but basically, you know, the scripting mechanisms of IDA allow you to kind of write that sort of functionality and just look for those sort of suspicious things. Let me try and figure out where we were here, and then hand this back over. All right.
So, just some final concluding thoughts about you know, what we found with our backdoor research of how these things played out. You know, backdoors are, if you're an ISV and backdoor is found in your code, it's typically worse than a vulnerability being found in your code because they're typically trivially exploitable. So you're not going to have to write a tool to exploit it. You can usually do it at the command line or, you know, through the web browser. So they're always going to have a high severity because of that. The other factor is if a backdoor is detected in your code, the press treats you very differently than if a vulnerability was found in your code. If a vulnerability is found, it's, you know, oh, your developers need training or you're just not so good at coding. But if a backdoor is found in your code, it looks like you're basically incompetent. You don't have control over your development process or your, you know, your distribution points. So for those two reasons, auditing for backdoors is something which is probably more important than just auditing for regular vulnerabilities. So if you're an ISV or you know, you're on an open source project, it probably makes a lot of sense to audit with this along with your vulnerabilities. So, you know, when you're going to look for it, it's probably a good idea to scan your code before you release it. Another case is when you're doing, most people don't write 100% of their application. They link to libraries, whether they're shared or static, different application frameworks, different vendor libraries, database libraries, graphics libraries. So those could contain backdoors in them also. And that's a case where you're sort of acceptance testing binary code when you decide to use another party's package and make it part of your application. So this is a place where you're going to have to do it at a binary level. And then just a final thought is there actually is another way that it can be, a backdoor can be inserted. It's not necessarily a distribution point of the code. It could be your compiler or your linker has been backdoored. And so the tools you use to turn the source code into the binary could actually be inserting the backdoor. And this is something that Ken Thompson wrote a paper on, Reflections on Trusting Trust, where he actually did this to the Unix operating system, sort of as a proof of concept. He backdoored the compiler, so whenever it compiled the login program, it put in a special credential in there, so he could always log in. And at the time, binary analysis was really not conducted. There weren't good tools to do it, and he kind of posits in this paper that we can't really trust any code because the tool chain could be compromised. So how would we ever detect the backdoors? But now here we are in 2007, and there's a lot of good binary analysis tools out there, and so it would be possible to find some of these backdoors today. So that was all we have for our presentation. I guess